I'd like to take a few minutes to discuss nucleophilic aromatic substitution. And we can contrast that to what we've been talking about up until this point, electrophilic aromatic substitution, where we brought in an electrophile and the ring acted as a nucleophile. In this case, we bring in a nucleophile. We know that NaOH is a source of the strong nucleophile, strong base OH minus hydroxide. And in this case, the ring will act as an electrophile. So we have now reversed the reactivity of our aromatic species. There's a couple of requirements in order to have NAS. We need a powerful electron withdrawing group. And by powerful, I mean one that can actually accommodate a lone pair of electrons, not like bromine or chlorine, which is simply an electron withdrawing group via induction. We need something that can accommodate electrons via resonance. We also need a good leaving group on the ring. And lastly, the leaving group must be ortho or para to the electron withdrawing group. And we'll see why that is when we explore the intermediates formed during this reaction. So we have set up this ring. We've got a powerful electron withdrawing group, NO2. Sometimes carbonyls are acceptable in this case too. Multiple carbonyls would be better. We have a good leaving group in the form of bromine that is para to the nitro group on this ring. So we have a good candidate for nucleophilic aromatic substitution. Let's explore the mechanism. So we start with hydroxide, and the hydroxide is going to attack the carbon bearing the leaving group. Now if you want, you can draw some resonance structures of the starting material that puts a positive charge at this carbon because electrons are withdrawn through this pi system into the NO2 group. So you could put a positive charge there if you wanted to. You could put a positive charge here or here. So that can support why I drew my nucleophile attacking at that position. And of course, if I just leave the arrows right like that, I have too many electrons around that carbon. So let's go ahead and move one of the pi bonds out of the way. So now I have two bonding partners at the top carbon. I've got a negative charge here, and I've got my NO2 group. And we can show that this negative charge is stabilized by resonance. I'm going to pause my recording here while I draw the rest of the resonance, and you can pause the video, draw the resonance structures, and we'll see what we've come up with together. And now we can see my 4 resonance structures here. The most important structure is this one, because it is a 4th additional resonance structure. You can see that we have a negative charge on 3 different carbons in the ring, but in this structure I've put that negative charge out onto the nitro group. So this one shows why we need an ortho or para relationship between the leaving group and the electron withdrawing group. That's so we can obtain this 4th additional resonance structure. And so I've stabilized the anion that's formed when the nucleophile attacks. And now we are ready to draw a final arrow push, which shows the leaving group leaving and regenerating the aromaticity. And one more point here is that we are in strong base, and we've just made a phenol. So this phenol is not going to survive the strong base. So another equivalent of NaOH comes by, and actually let's make this a better bond. And we're going to deprotonate that phenol to make a phenoxide, especially when that phenoxide has a strong electron withdrawing group attached to it. It's going to be a very easy, rapidly forming proton transfer step. And then you see the second step that in my original reaction uses H3O plus to protonate the phenol just to make sure everything is back to neutral. And so here's my product. I have substituted the bromine for a strong nucleophile. In this case, it was the hydroxide anion. And this is called nucleophilic aromatic substitution, where we are using a different nucleophile, and the ring is now electrophilic because it has a strong electron withdrawing group attached. Let's look at one additional example. Let's remember that we need a powerful electron withdrawing group. I've got 2 carbonyls attached to my ring. Those are both good electron withdrawing groups, and together they contribute even more electron withdrawing nature to the ring. I have a good leaving group, and that leaving group is ortho-para to the electron withdrawing groups. It's ortho to this one, it's para to this one. So let's try to predict what the product would be. You can see we're set up exactly the same as before, NaOH in heat, followed by H3O+. So we're going to predict the exact same mechanism, and I'm not going to draw that mechanism for you. I'm just going to substitute the chlorine for an OH. So this is a way to make a phenol, actually. We haven't really learned how to make phenol or put an OH group on a ring, so this is one way to do it. You could use nucleophilic aromatic substitution as long as your ring has an ortho or para strongly electron withdrawing group.